Okay, so for FP, I'm going to split up the collection into three parts, into three videos, because each of them is quite long. So each of them, let's make it roughly about 20 minutes per video. Okay, so for question one, it's relatively difficult with the unfold. So we have the function unfold is of type um, first we have a function from A to maybe BA, and then we have our input A, and then we go to a list of B. So we have unfold of fx is equal to case of fx. If fx works, we have just yz, so we have y and unfold f of z. And if that doesn't work, then we just have an empty list. So for part A, we want to find f such that unfold f is the identity function on list. So that basically means our A is an input list, and then we get out a list. So type B should be A. It can be anything. Type A has to be a list of B, like of the same type of Bs. So that's why type A has to be a list. So we know that when we define F, we have a list and it goes to maybe A of a list because we just basically put it into the same type and replace A with list. And it said we want the identity for lists. So for a list, it means that if it's empty, then we have nothing, we're just at the end. And if we have an element, that means that the first element is just X. And then the remainder is the rest of the list, which is excess. So that's how we have just X excess. Okay, so in part B, we have find f such that unfold of f of x's equals to the concatenation of x's plus y's for all lists. Okay, for this, we kind of see the definition here that this is just basically putting the front thing into a list. So that's pretty good. The unfold already takes care of that. So what we need to do is essentially just map out the different scenarios and deal with it. We first define the type. The type is because we first start off with x's and y's. Both of them are lists, so then that's why we have a list. And then we should output either just the case of it, which is nothing, or we have or an element, and then this is the rest of the remainder things, which is also in the form of a list and a list. So for our f, we have four cases over here that I list out here. These are the four cases. And for this, it's better to start off with the most simple case where both are empty. If both are empty, there's no talking point. It's just nothing. And then in our second case, we have excess and then an empty thing, or excess and y's. So then for these two cases, it's covered in this case because we really don't deal with y's as it could be anything. And then our x's, we just put the first element into the just x, and then we deal with the rest over here. And then for the last case, third case, that's when we have the empty list and then we have y's, y and y's. So then we just put the y in front and we keep the empty list here. And this way we cover all the cases because no matter what, we just kind of put the first element there. And if there's nothing, then we just return nothing. Okay, so that basically gets, because it concatenates, because no matter what, we're going to first try to take elements from X, and if X doesn't work, then we take elements from Y, and if that doesn't work, then there should be nothing. So then our next question is the function fold is of this type. That makes sense because we have A to B to B. This is the function. We first input the B, then the list of A's, and then we should get out a B. I think it relatively makes sense because B is, and this is fold R because we just have A, B, B. If it was fold L, then it would be B, A, B. Our B is just our initial value, our A is the list of elements we input, and then B is our final result. And then the function, because we have let's say fold f of x, empty is equal to x, so that's our base case. And then we have fold f of x of y and y's is equal to this case. So we take out the f, we apply it to y, so we have that outside, and then we have the remainder case, recursive case, which is fold f of x, y's. So I think that's relatively straightforward. Say, fold of A, B, B, I think it's just how I understand it is that we just take out whatever element, we also take the initial value, then we get what the B is. Let me double check on that. I think it's the case. Let me move this over. Fold F of, let me fold Y is A. Let me double check on to confirm that it's indeed the case for R, right, and B, A. This is just recap. I think once upon a time I did know this, but I'm just confirming this if it's the case. Okay, let's wait for a bit. While that's going on, let's go to part C and I'll explain that. So the function take while has the type of this. So we have a function that goes from A to bool, then we're given a list of that function, and then we're supposed to return that list when that function is applied. So that's basically take while is just we're just going to check each element of the list when the predicate holds true. If that fails for the first element, we stop taking it. For the predicate, is it possible to find f of x such that this thing is equal to fold of this? So basically, we're trying to write it in the form of a fold. In terms of writing it in the fold, indeed, it's possible to do it because we just have a predicate and we think of the fold as every step. We kind of have our x, which is our current value, and our accumulator from the past. So if our thing holds true, then we would just take our current element, then the accentuator. But if it's at any point it's false, we just return an empty list. So we're done with the rest, so we don't care about it. So that's basically how we do the thing. It's just check if it's true, add. If it's false, we stop immediately. And it works out that way. And the way we write it, it's pretty straightforward. And our starting value is just an empty list because there's nothing in it at first. So part C is pretty straightforward. Okay, let's see what the explanation is for here. Okay, I'll paste over the answer over here. Like why it's ABB versus BAB. Take a picture and then move it to this document. Okay, copied it. Now I should be able to paste over here. So okay, let's go into detail why it's ABB versus BAB. So for right fold, the right fold stands for a fold R or fold, and it processes the list from right to left. So it essentially replaces the list constructor disk and the function with the empty list with the base value z. So we have fold of f of z of whatever list. So it's just basically applying the function first at x3, then x2, then x1, like this. So the type is ABB because if we look inside, f of x3z. So our first element is x3. x3 is of type A. Then we have our second argument, which is our accumulator result. So that's our type B. And then our result should also be the accumulator B. So that's why we have the A, B, B. And then for the left fold, it's from left to right. So it would look something like this, this, this. So it goes from, it's stuck in the, it's like a middle element that we replace. So then this part, our accumulator is actually, that comes before the value. So then we have the accumulator first, then the actual value. So it's just A and B swapped, but the result always should be the same with B. Okay, now I remember why that was the case. Okay, so now moving on to part D. The function drop while of this type is the same as take while, basically. Drops element from the beginning of the list as long as the given predicate holds true. Once the predicate returns false for an element, it stops dropping and returns the rest of the list, including element that failed the predicate. Given a predicate P, it's possible to find a fold. If it's not, then definitely right. So the answer for this question is unfortunately no. Even though it seems like it's exactly the same as take while, we kind of can't work around this because we have the first part of the list that's true and the rest of the part of the list that's false, right? In the earlier case, when we checked when it's true or not, we can keep track of the list. Whereas if it's px is true, then we want to discard x and return the accumulator. If p of x is false, then we stop dropping and return the entire current list. But because we don't necessarily have access to the tail, only to the accumulator, so we cannot unfortunately write this code. Because the idea is that before this one works because we just take the accumulator to be the front thing and we just check the condition. And if it doesn't work, we can skip the rest. Whereas if here we have something that's true, we can't just say, oh, we're going to return the rest of the list. It's a recursive step, so we don't know when it's actually going to end. And we don't have access to the tail, we only have the accumulator. So that's why it doesn't work out. Okay, moving on to part E. Okay, part E is like a much bigger question, and it's a standard proof. So we're given this. We have the fold out function, which is pretty straightforward, and a scan out function that basically is like searching each element of that list. It goes over each one. And then we have our inits function. Inits is basically we're generating the function one element at a time. Yeah, should be. Um question, yeah, I want to check 1E so that I have a better writing. But essentially the idea is that inits just generates a list of lists of each permutation every time first like the empty, then the next one with one element, then two element, then three element from left to right. And scannout basically is just the combination of here we want to prove that the map of fold L of fx composed of inits is equal to scannout of f of x. So basically this is the idea that we have our inits, so we generate all the possibilities, then we kind of just apply the map of fold to each one. So that's the result of each one applying that. And scannout is just basically doing that each step. So we want to make sure that we prove any auxiliary results. Obviously, this is a proof by induction. There's kind of no way around that. So we want to prove this statement, and then because we just have a composed and we're not having the argument, we can just rewrite this as essentially we just add a wise argument so that we have a list to work the inits on. So because we added Y's, we would want to do induction on it because it's the only kind of list we have access to, right? So we have the base case, which Y's is the empty list. On the left-hand side, we have map of fold f of x inits of empty list. Because we know the definition from earlier that inits is just empty is just the nested empty list. We have map fold of f of x of this thing. And then by definition of this, we're just applying fold of fx onto the empty list. So we have inside the list, we have fold of fx empty. And by definition of fold L, we're just putting the x in. This is just the value of x. So we have the a list with one element of x. On the right hand side, we know that scan L of f of x empty list. We're just looking at one thing, so we just have the empty list. I mean, the list with X. Let me double check. Am I doing this correctly? Yeah, I think we're doing a pretty good job here. Scannow is just basically if we have that one case, the base case, it would also be the base case. Okay, so we next have our inductive step. So our induction hypothesis is that the original statement map of photo of f of x in its y's is equal to scan f of x y's. So we want to show that for the next step, y of y's, when we have one more element in the list, it still works out. So on the left-hand side, we have map photo of fx, and in its y, we have this extra element. So by the definition of inits, um, because we see over here that when we have x of x's, we have the empty list cons map of x's in its axis. So we can just write it using that definition. So then we get this thing, just expanding out, sorry, this definition. And then next we want to apply map, definition of map. Obviously, I should definitely, because they said auxiliary things, then I should know that map of F composed of G is equal to map of F map of G. So here I have fold of F of X, um, and then I compose it with the empty list because I have a map here. I just apply this fold F of X to the first element of this array empty list over here. I just apply this over to here. And then next I have the remainder, which is map y of this thing. And I also have to apply this. So basically there's applying map to each one of this photo f function. And then this leaves me with I have my x in front because fold f of x of empty is by definition of this is just x from here. This thing is just equal to this. Next, we have map of photo of f of x composed of y of inits. Because this is the case because we have map and map. Let's use a different color. Let's use green. Map and map. So basically we have the map law that we use here. And I should definitely prove that with induction. That was not done here, but essentially I do need to prove that by induction. And next what I do is in here we have the map photo of f of x composed of y. This thing, so I just say that if I have a z's here, if I have something over here, then it would be this form. And then on this side, I could say that photo of f of fxy is equal to the thing applied to z's. So I think this step came from this is kind of difficult. I am kind of having trouble kind of explaining why this is the case. So I have X, and then next I have map. Mm, this is just copying. I can understand from this point. And now I'm trying to see photo of f of x composed of y, and then if it's z's. Okay, so this sentence is just an aside that I use. Like this is not fault. This step should lead to this step. This is just an intermediate step where I just said photo of f of x y's with the z's is equal to photo of f. This is just applying the definition of photo essentially because I'm just applying photo of f of x to the y so that I get my photo of f which I keep my f, and then I apply it to the middle element of the base case, which is y. So it's f of x, y. And then I have my remainder of the z's that I need to deal with. Okay, so that makes sense. And then I would go back to my original equation. I still have my x here that I copied from before, my map of fold L f of x, y, because I just composed it together. F of x composed of y in front would just be the same equivalent of saying fx of y. And then I have my inits of y's over here. This step is still not clear. I'm gonna make sure I understand it. So this is part E. Let's see. Yeah, I try to simplify it using the base case, accentuate, accumulator map photo f of map of x, and it's map composition law, x accumulator. Yeah, I got to that step. It would be accumulator of x of y's. I guess this is the auxiliary step that I sort of skipped here, but essentially, let me screenshot it and bring it over here. It's not the same notation because I just used an AI to generate it. So we're gonna have to work it out ourselves. What I was thinking at the time when doing it. I think that time when I was doing it, I definitely just kind of used my own notation and I walked through it pretty quickly. But right now I'm trying to decipher. I did not write out my proof neatly, so I skipped too many steps. I'm trying to bridge what I was thinking at the time. So in the auxiliary step over here, we do have our fold L, f of thing, and then we have our x was just our y, and then we have this function. This can be thought of as if we apply it to any list, then we would have this thing over here. Um, I think it was just because we moved it into this thing. And then using the definition of fold L, we kind of see that our accumulator, we're going to want to apply the f of accumulator of x, and we're left with y. So this is just the definition. So then we can get what we need from here, plugging it back. So I think we could do something similar in our case. We have x composed of map of fold f of y. So then that was why we brought the z's in. When we brought the z's in, that made our thing slightly easier. Then we have y composed of z's, so then we would just apply. It should be f of x of y. So then I'm kind of confused because yeah, x is our accumulator, y is our new elements, and that's why we have x of x, f of x of y. Yeah, that makes sense. And then we have the z's. So then when we put it back, this is just, we kind of just remove the z's on both sides. So we get fold out of f of x, y. Yeah, that makes sense. Okay, moving on. So by the induction hypothesis, we said earlier, because we got it back to where was our induction hypothesis? We wrote it down here. That's this. So we finally got it to the form we want. Something of the form map, fold, and except it's this thing over here. So then by induction hypothesis, this is just equal to that. Pretty straightforward, I'd say. And then on the right-hand side, we can say that scan L of f of x of y, this is just the initial starting point, and then we can just use the definition of scan L that they said, and we can just extract out the definition of scan L is that if we have such a case over here, we can say that we can put x in the front, then we have scan out of fx, y's. So we can just extract out x in the front, which is using the definition directly. So we have x of scan out of f, x, y. This is just using the definition they give us. And we see that this over here is the exact same as we got over there from the left-hand side. We have the same expression. If we have the same expression, the left-hand side equals the right-hand side, so it holds for all lists. Okay, so next, am I even recording? Okay, yeah, I am recording. Okay, good. We're looking at part F. Let's go back to part F. So what is a computational complexity of the left and right-hand sides of the equation in E, assuming F has constant time complexity? Express your answer using big O notation. Okay, so F is quite easy, I'd say. So we're assuming F takes O one time, and that N is the length of the list. On the right-hand side, it's linear because the scan out, what it does essentially is for everything as we build up the list, we're just kind of taking the photo of each one. So let's say that this is the first element. Then for the second element, we just kind of add the accumulator, the new result to the accumulator. So we're always just doing one step at a time. So as we progress through the list of 2 element, 3 element, we just produce the value of fold every time for that as we do scan out. So it's just iterating through the list. So this is just ON. Whereas if we do the fold, first inits, then fold, then we have to first do the inits. Inits, we have to go through the list and create the things, right? And then because inits, we have to, for each element, go through it. Then it's an ON squared operation because we have first 1 element, then 2 element, then 3 element. We have to just kind of go back each time to create that. And then we have each one has to fold because we have to, for example, this is 2 element, this is 1 element, this is 3 element. And then it goes all the way until, let's say, we have n elements inside here. And then this is what your inits do. It generates this. Then each one is applied to fold. So now we have to do this, then do this, and do this. And then each one has to go through n times. So then you have to do n times for this. There's endless, and each one has to do n times. So then we're talking n squared. Each one's like 1 squared, 2 squared, 3 squared, so on and so forth. That's n squared. That's quadratic for sure. So that's why the right-hand side is so much scan out is much better than using the fold and inits then fold. So the lemmas we have to use for this that I missed the proof was map F composed of map G is equal to map F of G. This is done with induction, and then this is just a definition of fold out, which I don't think requires any proof, but that's something that we should use. Okay, that's it for the first question. I think the first question was definitely a bit on the difficult side, because the unfold thing I had difficulty um writing the type and how to actually deal with it. On top of that, I'd say the fold part, the drop wall part was slightly difficult, but I got that part. And then part E was should be bookwork, but I think it's been a while since I did actually the proof. So I had a bit of trouble kind of following what my steps were. I think the major difficult part of this is just kind of knowing the definition for and applying scan because like scan f of x of list, this is a base case. If we have um that, it should be just this the thing of x with x, right? Okay, let's end it off here.